Okay, for the 8.1 quick check, I'm going to try to go through these answers. So the first one that says, for each formula, write what it's used for. Okay, so we're talking about C equals lambda times nu. And the idea there is that this allows us to go from wavelength to frequency and frequency to wavelength. So we can say this allows us to convert between the wavelength and frequency. Okay, so frequency. Okay, and that's the letter nu, and wavelength. That's the word wavelength. Okay, so it can convert between those. So if you know one, you can find the other. And you need the constant speed of light, 3 times 10 to the 8th meters per second. Okay, the second one here is actually two different equations. So E equals h nu, okay, but we also have E equals hc over lambda if we go back and convert nu into c over lambda and substitute back in. So both of these. So we get to convert. Okay, and we're going to convert between energy and wavelength and frequency. So if you know any one of those three, you can calculate the other two by using those equations. Okay, energy of level N. So this is the hydrogen energy level. So hydrogen electron energy level. So you can figure out any level, just put in the level N, 1, 2, 3, 4, 5, etc. And the last one here, this is if you have a moving particle, you can calculate the wavelength. Watch out here, this mass has to be in kilograms. Okay, now this is a V, this is not nu, this is velocity. Okay, meaning that these ones up here, that little V-shaped thing here, that's the letter nu, Greek letter nu. This is actually V, so velocity. So the Planck's constant divided by mass divided by velocity, and that mass has to be in kilograms. So this is figuring out the wavelength of a moving particle. Okay, let's actually do some of these calculations. Whoops. Okay, the first one here says a hydrogen emission spectrum. Okay, calculate the energy of n equals 5 level of the hydrogen atom. So we can use the equation here. So E of level n is equal to negative, and the number is 1. I have to go back and look up here. I thought that was wrong. 2.178 times 10 to the negative 18th joules, that whole number divided by n squared, okay, which is going to be divided by 25. Divided by 25, and that equals, I get 8.712 times 10 to the negative 21 joules. Okay, so that's the energy of that level. Okay, now I'm going to calculate the energy and the wavelength of the light emitted when an electron drops from level 5 to level 2. So first off, we have to go back and figure out what's the energy of level 2. So energy of level 2 is equal to negative 2.178 times 10 to the negative 19th joules divided by 2 squared, which is 4, and that comes out to be, okay, I just realized I made a mistake here. So up here I had negative 18, and when I got over here I said negative 19, which is totally wrong. So I'm going to make this a negative 18, and then this comes out to be negative 20. Okay, same thing down here. I'm getting this negative 19 in my head. So when I put that number in divided by 4, then I get 5.445, so I'll say 5.45 times 10 to the negative 19 joules. So calculate the energy of light emitted when it drops from level 5, okay, n equals 5, electron, drops down to level 2. So when electron drops down, it gives off energy. Okay, and we always do this as final minus initial. So I'm going to take my value from 2. So this number 5.4, negative 5.45 times 10 to the minus 19 joules minus, okay, negative, that's a negative. I'm goofing up. 8.71 times 10 to the minus 20 joules. Okay, and that's going to come out to be negative 4.579, so I'm going to make it 4.58 times 10 to the negative 19th joules. So I just subtract those two values and I get that energy. Okay, so that's my energy. That's one of the values. And then I want the wavelength for this. Okay, so I know that E equals hc over lambda. Okay, and so that means I can mush that around, so lambda is going to equal hc over energy, and I'm just going to substitute numbers in, so I'm changing colors. So h I know is 6.626 times 10 to the negative 34 joules times seconds, times c, which is 3 times 10 to the 8th meters per second, and that's all divided by my energy, okay, which is 4.58 times 10 to the negative 19th joules. Now notice here I do not want to put my negative in because that negative just means that energy is given off. There's no such thing as negative energy, so I just put in the energy and I work out the answer to this entire problem. And I'm getting 4.34 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. Negative 7. Okay, and this is a wavelength, so this is coming out in meters. And I could go through my joules, cancel out, seconds cancel out, so I'm left with meters. And so that is the wavelength of the energy that would come off, of the light photon that would come off when it drops from level 5 to level 2. Okay, for question 4, we're talking about the photoelectric effect, and the idea is that we're going to shine some light in onto our piece of metal, and we're going to put it in with this energy, and what happens is that it comes off, okay, with that kinetic energy. So we're saying that the binding energy, okay, plus the kinetic energy equals the light energy that went into releasing that electron. So we know the kinetic energy that's here, we know the light energy that's here, and we want the binding energy, so we can just see that the binding energy is going to be the light energy minus the kinetic energy. So that is going to be 6 times 10 to the negative 19th joules minus 2 times 10 to the negative 19th joules. So even without a calculator, we can see that that's going to be 4 times 10 to the negative 19th joules. And that is our binding energy. That's the energy holding it into the piece of metal. Now, would another electron with a binding energy of 5.0 times 10 to the minus 19 joules leave with a slower or greater speed than the electron in part A? Well, the idea is this is how much energy it takes to release that electron from the metal. So if this one takes more energy to release it from the metal, then there's going to be less leftover energy to be as kinetic energy. So what's going to happen is that our kinetic energy will be less. It's going to be a slower electron that leaves if that's the binding energy. And we could calculate it if we want to, but we don't have to. We just know that it's going to come off with less kinetic energy. Okay, the de Broglie wavelength. Okay, de Broglie wavelength, we saw that equation earlier, and that is that the wavelength is equal to h times c, equals h over m v, and that's a velocity in this case. Okay, so we know the mass is 50 kilograms. We know the velocity 2 meters per second. So this h we know is 6.626 times 10 to the negative 34 joules times seconds divided by the mass, which is 50 kilograms, and divided by the velocity, which is 2 meters per second. And we might remember that a joule is a kilogram meter squared per second squared. And we're calculating a wavelength, so when we get all done, we are going to get rid of our joules, we're going to get rid of some seconds. So we have seconds down here, seconds up here, we have seconds squared. Okay, we have kilograms, we have kilograms, we have a meter, we have one of the meters. So when we're all done, the answer is going to be in meters, which makes sense because that's a wavelength. And let me calculate. Okay, thinking about this for a second, I didn't really need to use my calculator because 50 times 2 is 100. So all I need to do is to divide this by 100. So the answer is 6.626, or we could round that off, times 10 to the negative 36 meters. And that is called the de Broglie wavelength of that running runner. And that's going to be totally insignificant according to the size of the runner. Okay, last one here is a quantum numbers. Okay, so for quantum numbers, we get a different color. Quantum numbers, when n equals 3, L has what possibilities? Okay, L can be anywhere from 0 to n minus 1. So L could be 0, it could be 1, or it could be 2. Now, if it's a 3s orbital, okay, the value that we're using is 0. L equals 0. Okay, for s orbitals, L equals 0. So L0, 1, 2, L could be 0, L could be 1, L could be 2, let's say it could even be 3 and 4. And if that goes, then it means the orbital is going to be an s orbital, a p orbital, d orbital, f orbital. So we just memorize that, L0, 1, 2, 3, s, p, d, f. Okay, but on level 3, there are 3 possibilities because there are 3 different kinds of orbitals, 3 different subshells on level 3. Okay, when n equals 4 and L equals 3, M sub L has what possibilities? Okay, the M sub L possibilities come totally from the 3. So it could be negative 3, could be negative 2, could be negative 1, could be 0, 1, 2, 3. Okay, there are 7 different values because there are 7 different f orbitals. Okay, when we say L is 3, we're talking about f orbitals. So this is a 4f orbital we're talking about. And f orbitals come in 7s because there are 7 different values for M sub L. Okay, we have a p orbital, 5p orbitals, so n equals 5. Okay, a p orbital, we know that L equals 1. And if L equals 1, then the values of M sub L could be negative 1, 0, and positive 1. And that's why p orbitals always come in 3s. Okay, so if I said 5p orbitals, there would be 3 of them. Okay, one would be x direction, one y direction, one z direction. So 3 values of M sub L, there are 3 different p orbitals. And that is the quick check.